Hello and welcome back to Fullerton College's pre-press class. This is Professor Ben Hewitt. We are talking about color theory, and in this second video in our series, we're going to define a little bit more about light. We've so far discovered that color is a phenomenon or an experience that we have as our bodies, specifically our eyes, encounter different types of light in the same way that we experience things like smell and flavor. Those are things that are immensely personal. How something tastes is something that only you know. No one else can compare how something tastes to how you taste it. It's entirely your experience, the same way the color works. But we're going to look at the measurable, quantifiable parts of color now, the parts that are scientifically provable. Now, color for us is a reaction we are having. A reaction is maybe the wrong word for it, is a experience we are having as we are coming in contact with different wavelengths of light. So what is light? Well, science doesn't know exactly what light is. We do know that light is, and we also do know that light works in two different ways. Light acts as a particle sometimes, which is to say it acts as if it's physical matter. And other times it acts as if it is pure energy. Now we're going to work on the energy side because that's the side that seems to matter more to our vision systems. So how we see things is a response to sensing the energy of light. So like most energy, at least electromagnetic energy in this world, in this universe, can be defined as a wave, which is a repeating pattern of motion. The energy has high points and low points, graphically speaking. And what matters for us is the wavelength. The wavelength is a distance between two peaks, or peaks is an easier part to measure. Any part you can measure of the wave from one to the next wave of the same size. So it's easier to do from the very tops to the very bottoms because that's something you can see visually. So on that little rainbow on the right of the screen, you can see it goes up and down and up and down. The distance between the top peaks is the wavelength of any one of those things. So depending on how far apart those waves are, our eyes and our brain interprets light within that particular energy band that gives that certain wavelength as a certain color. Only a little tiny narrow piece of the entire electromagnetic spectrum is visible to our eyes. We call that the visible spectrum. Beyond it, going with smaller and smaller and smaller wavelengths, below what we can see, you get ultraviolet, and below that you get X-rays, and below that you get gamma radiation. Quite a bit of very small frequencies are actually very dangerous to life. X-ray and gamma radiation, even ultraviolet radiation, can cause all sorts of biological problems for our bodies. Quite a bit of space travel involves shielding us against such things, because without an Earth's atmosphere, which filters most of this out, you're up in orbit, you're exposed to all this stuff, and those types of radiation can be pretty deadly to humans. If you go on longer wavelengths beyond what we can see, you get to red, and then beyond that there's infrared, which is kind of like heat, and mostly it's known nowadays because of heat vision and things like heat-seeking missiles and night vision type goggles. That's the near infrared. There's also far infrared, which is beyond even what those things can sense. And beyond that, you get into radio waves, like the types of things you listen to when you're driving your car. Okay, so that's most of it. That little narrow band in the middle, which is represented by a rainbow in a picture, a diagram of an eyeball, that right there is a visible spectrum. So that's between 400 nanometers, which is actually the distance. 400 nanometers is how far apart the peaks or the troughs are on that wave, and that's blue, or to 700, which is red. So the very small difference between 400, a 300 nanometer difference is the part of the spectrum of all radiation that we're able to see with our eyes. Now, some people can't distinguish between primary colors, which is to say they can't see the difference between red, green, and blue. We're going to talk about those primaries, what they mean and where they come from a little more later. But note that up to about 10% of males on this planet are not able to see all colors. They don't sense a difference, which is to say they don't sense a difference between some of the different primary colors. Most typically, it's red and green that they can't tell the difference between. It has to do with parts of your eyes working Properly is not the nicest way to put it, but with the functionality of the rods in your eyes. Only 0.5% of females are color deficient. That's one of the reasons all the old jokes and tropes about women understanding the colors they want to paint the house and their husbands, the men in their lives, having no idea the difference between those different shades of blue, and there being all sorts of hilarious hijinks and misunderstandings that make up most sitcoms comes down to the fact that actually men are less sensitive to color, or males, I should say, sorry. So color perception. It's important to understand what type of color perception you have. Are you seeing the whole picture or are you not? It is totally possible to still work in visual arts and graphic arts if you're slightly or majorly color deficient. It's possible. However, you should know about it. You should know when you're not seeing the whole picture, because that will save you some embarrassing times with clients where you're pretty sure it looks fine and they're not sure why you've done this. I have some stories I can share about this from an old job of mine in a moment. And no, this is not actually a printing job. Anyways, here's the people who should know about this. The people who work on production. Definitely the customer service representatives, because they have to communicate with the client from what they're seeing and tell the designers what they're seeing. Sales personnel, so they know they're selling the right thing. And the client should know if they're able to see it. Yeah, good luck getting them to take a color deficiency test for you before they buy something from you. It's a little hard to control. You can't control the people. It's really hard to get them to do these things. There is a color deficiency test available here. The Ishihara is kind of the standard. And if you think about it, or when you see it, you'll understand what I mean, because it is what you think of when you think of a colorblind test. The webpage here, richmondproducts.com, is a place you can see it. There are all sorts online. And I've also posted a link to this class that will take you to a fun one where you arrange colors and it will tell you how good your sensitivity is. Here's a sample from the Ishihara color deficiency test. It's just a solid green circle. I'm kidding. There is a red number 6 in the middle of the green. The way these tests work is they make sure that they have a slight variation wow, the word fell out of my head, in brightness. And light to dark contrast between the circles, and they make sure that those are the same levels of bright to dark through the whole image. And the only variation that makes the image in the middle of this, in this case a number 6, is the fact that there are some reddish spots and some greenish spots. They've even gone a little bit more insidious on this, and the greens are pushing olive and the reds are pushing brown, and olive green and brown kind of meld together sometimes, even if you're not color deficient. So it's really checking to make sure that you are sensitive to those differences. So, story real quick from an old job of mine. Back when I used to work for a maritime museum, really fun job, by the way, teaching kids how to sail ships, good times. One of my coworkers was massively color deficient in his vision. Nice guy. I still see him sometimes. Cool guy, fun guy to work with. But not even a but. And he couldn't see color very much at all. So there are 2 examples involving Al, good friend of mine there. One of them is when most of the time he would listen to us. So he would talk to his coworkers and friends and double check before he went out in public wearing something. So like we're all wearing white dress shirts for a nice event, and his undershirt is construction safety orange. To him, it just looked like a white shirt. Couldn't tell the difference between his white shirt and his orange shirt. So there he is with orange blazing through his white dress shirt. And we're like, Al, we need to help you out here. So there's that one. And there's also another time where he was wearing these blue pants. At least he thought they were blue. They were, in fact, Barney the Purple Dinosaur purple. And we're like, dude, those are purple pants. He's like, no, they're blue. So sometimes he listened, sometimes he wasn't. The whole point of this is if you know that you're not able to see some things and other people can, ask other people, and then you overcome the deficiency. It's that simple. We are a communal creature. That's one of the advantages of living in a society where other people can help overcome your weaknesses and you can work together for a common good, like not wearing orange undershirts under white shirts. So let's talk about color systems. The additive color system involves light. It's additive because you start out, your blank canvas, so to speak, in the additive system is darkness. On top of darkness, we paint with light. That sounds really, really amazingly cool, but it's just saying that for the additive system, we're talking about adding actual light sources together. This is like stage lighting. Also, you know, think about it like the computer you're currently looking at while you're watching my video. TVs, cell phone screens, anything where you are staring directly at a light source that you're seeing colors in, that is additive lighting. A white light contains, hopefully, even proportions of red, green, and blue light. That activates all three types of cones in your eyes, because in your eyes, remember we have our rods and our cones. Our rods see lightness and darkness. Our cones are sensitive to one type of cone in your eye is sensitive to green, another type is sensitive to red, and the third type is sensitive to blue. So we're talking about using primary colors and mixing them together. Well, I'm not sure if any other creature in the universe would see it that way. What we are doing is creating things that fool our vision specifically. We realize that when we look at things, we're seeing a mixture of how much of those three different colors of light show up to our eye. So we can also directly pump those three colors in the same proportions to each other and simulate those colors, as seen in my "There is no yellow" video that I shared. Not yellow. There's no yellow on this computer video that I shared with you as well in this particular course, because yeah, your computer monitor has red, green, and blue pixels, or cells really, that make up your images, and there is no yellow cell. Yellow is something you see when you see red and green in equal proportions, and no blue. Anyways, so those are things that you can see the additive system on. Here is a cool diagram. I really like these. This shows you how additive light works. The background is black. You start adding light together. You add red, you add blue, you add green, and then you kind of see white. In fact, after he falls from grace, I believe the wizard Saruman the White makes some comment about his Saruman the many-coloredness and how isn't white light broken down into all the colors of the rainbow? And you can see that too. If you take sunlight and use a prism, you can diffract it out and make a perfectly good Pink Floyd t-shirt. I'm sorry, make yourself a perfectly good rainbow using diffracted light or refracted light. So prisms can split the spectrum of white light back into its components. You see a rainbow, or less than a rainbow if there's not a full spectrum present. I'll show you a trick on that one later too in another video. Anyways, so this is also one of those weird things where you mix things different than you'd think you would mix them. For instance, if you mix red and blue, you get magenta. If you mix red and green, you get yellow. If you mix blue and green, you get cyan. And when you think about mixing, you guys are immediately thinking about paint, and it's throwing you off because these are not mixtures you're used to seeing. But if we talk about it in the more biological sense, it might make sense. When you are seeing magenta, when your brain and your eyes tell you that you see magenta, what you are really seeing is an equal amount of red and blue light, but you are not seeing green light. When you are seeing yellow light, you're seeing equal parts of red and green, but you are not seeing any blue. And if you see cyan light, that means you are looking at green and blue light, but no red light, because that means in any one of these cases, for those secondary colors there, that only those parts of your eyes are being activated. And in the case of magenta, the cones that sense green see nothing. So what your brain is telling you is, hey, I am getting responses on these two wavelengths, but not on that one. And that color codes that information for you, so to speak, as magenta. Now, subtractive, that is interesting because it is inverted from additive. We're going to talk about that in our next video. So thank you for listening. We're going to come back in and look at this in more detail. Talk to you guys soon.